Hello, today we're going to start section 4.6, and what we're going to be doing is sketching curves. What's interesting about this section is we're going to take everything you've learned, going way back all the way to like Algebra 2, Pre-Calc, and everything we learned this year, and we're now going to put it all together into one problem for us to sketch curves. Make sure you're filling in this packet very detailed because it will count as a quiz grade at the end. Now you will need to know these 17 things in order to graph each thing. Let's start filling them in now. The first thing you need to know is how to find x and y intercepts. If you forget how to do that, you're going to plug 0 in for the opposite letter. So if you're looking for the x-intercept, plug 0 where the y is. Looking for the y-intercept, plug 0 in for the x and solve. Next, you need to know how to find the domain. Remember, for polynomials, the domain is all real. If you have fractions, make sure the denominator does not equal 0. If you have a square root, what's underneath has to be greater than or equal to 0. So keep those in mind. Next, the range. Sometimes it's easier to do the range after you graph, so think about that one. Next, symmetry. Some of these things you're only going to do if it's easy, and symmetry is going to be one of them. If you plug in negative x and you get all this, you get the opposite, every term goes opposite, then it has origin symmetry. But if you plug in negative x and you get the exact same function back, then it's going to be symmetric with the y-axis. Next, you have to figure out how to find the VAs and any holes in the graph. Remember, the VAs are the non-removable discontinuities, and the holes are the removable. And how you find them is you're going to set the denominator equal to 0. And again, if it removes, it's a hole. Doesn't remove, it's a VA. Next, find any HAs or any oblique asymptotes or slant asymptotes. And this is where you're going to use your power rules. So look at your powers. And if it's bigger on top, then there'll be none. But there could be oblique if you're bigger by 1. If it's bigger on bottom, then the horizontal asymptote is at y equals 0. And then if they're the same, you're going to look at the coefficients, and that'll be your horizontal asymptote. Next, you need to find the first derivative. After you find the first derivative, you're going to use that to next find the critical numbers. And a reminder, to find your critical numbers, you set your first derivative equal to 0 and equal to undefined. Once you find those critical numbers, you're going to want to use them to find where the function increases and decreases. If you know where a function increases and decreases, you can then decide where your local mins and maxes are. Then we move to the second derivative. After finding your second derivative, you can then list your PPIs, which you get from doing the second derivative equal to 0 and second derivative equal to undefined. Then we can decide where we're concave up and concave down. If concavity changes, we can then list our points of inflection. You can do the second derivative test to help with your min-max points. You should also think about, is the function differentiable, and if the function is continuous. Now at the bottom, I'm just going to list a couple things. These are the things you definitely must do for every graph. You have to do that domain. I need to see any asymptotes. for asymptotes, the vertical, horizontal, any obliques, any holes in the graph. Then go ahead and move to your first derivative, which would lead you to your critical numbers if you're increasing, decreasing, and your mins and maxes. Go ahead and do your second derivative. I need to see that, and that'll tell your PPIs, your concavity, and then if you actually have PIs. Things that you want to do if it's easy, because it's going to make graphing a lot easier, your x and y intercepts. And what I mean by easy, if you're going to have to do quadratic formula, that's not easy. Factoring, definitely. The next thing you want to do is check for symmetry. Again, it's going to make graphing half as easy or half less hard, because you only have to graph half of the graph and then you can reflect if you have symmetry. Now let's try one example completely together on the video. You can always refer back to this for later in the packet, but we will do quite a few of these problems together in class. So let's look at example 1. We have a simple polynomial. Let's start off by the domain. Since it's a polynomial, the domain is just going to be all real. The range will be easier after you graph it, so we can fill that in later. Symmetry. One shortcut for symmetry is look at the powers. I have a power of a 3, which is odd, a power of 1, which is odd, and then 0. So it's kind of mixed, even, and odds, so there will be no symmetry. It's just a polynomial. There's no denominators, like it's not a rational function, so we'll have no VA and no HA or obliques. To find the x-intercept, you're going to put 0 in for the y. So trying to factor this cubic is not easy, so we're not going to do x-intercepts. But you can plug in y-intercept. Put 0 in for your x terms, and if I put 0 in for each of those, I'll get 2. Next, we're going to find the first derivative. Simple power rule here, so we'll get 3x squared minus 3. Ask yourself, when will this be undefined? It's a polynomial, so none from there. When will this equal 0? So I'm going to equal it to 0. I can add 3 to the other side, divide by 3, and square root, I'm going to get plus or minus 1 as my critical numbers. Now let's find the second derivative. Second derivative will simply be 6x. When is that undefined? Never. When will this equal 0? When x equals 0, and that'll be your possible point of inflection. Now let's move down to the table. We're going to draw our number line above the table. Place your critical numbers and your PPIs. So place all of them onto the number line. Next, when you fill in the intervals and your critical numbers and PPIs, you're going to list everything on this top row, not just your intervals. So we're going to do our first interval, negative infinity to negative 1, and then place your first critical number, negative 1, in the box. Then our next interval, negative 1 to 0, and then our PPI number, 0. Then our next interval, 0 to 1, our critical number of 1. And then again our next interval from 1 to infinity. Now in the f of x column, you're going to find the function value at your critical numbers and your PPIs. So you don't need to fill in this box here where the intervals are. So you can scribble them out, make it like a checkerboard. Plug negative 1 into your original function to figure out the y coordinate. After plugging negative 1 in, we'll get 4. Plugging in 0, we'll get 2. And plugging in 1, we'll get 0. Now our testing points. A test point between negative infinity and negative 1 will be negative 2. You won't really need a testing point here. You're going to actually scribble that one out. A point between negative 1 and 0, we'll do negative 0.5. And then you can checkerboard this one. A point between 0 and 1, positive 0.5. And then a point between 1 and infinity. Now you're going to put your test points into the first derivative. So sometimes it might be useful to rewrite your first derivative down here. And remember, the factored form would be nice, or the original form, it doesn't matter. And let's plug in our test point. Plug negative 2 in. and calculate whether the sign will be positive or negative, and we're going to get a positive. Next, you can plug your critical number of -1 into the first derivative, but you should know what that's going to give you. It's going to give you a 0 because that's exactly how we got it, this number, -1. Plug in the test point -0.5 into the first derivative, and we're going to get a negative. Now we're going to plug in the 0. So if you don't have a test point, you're actually plugging in the numbers we have in the top row here. So plugging in 0, I'm going to get an answer of a negative. Plugging in 0.5, positive, into the first derivative, I will get another negative. Plugging in 1, because I don't have a test point, so I'm actually going to use the 1. I already know I'm going to get a 0 because that's how I got the 1 from doing the first derivative equal to 0. And then I'm going to plug in test point 2 into the first derivative, and that's going to be a positive. So you can see I have a nice pattern here. Where the zeros are, that's where the pattern changes. Positive, 0, so all three of these will be the same, all those negatives. Now let's rewrite our second derivative, which was 6x. So for the second derivative, we're going to plug in our test points or our critical numbers and PPIs into 6x. So plugging in -2 is going to give us a negative. Plugging in -1 is going to give me negative. Plugging in -0.5, I'll get a negative. Plugging in 0, I actually get 0. Now let's plug in positive 0.5. I get a positive. Plugging in 1, I get a positive. And plugging in test point 2, I get a positive. So now let's make our conclusions. From -infinity to -1, it's going to be increasing because it's positive, and it's in a concave down shape. Here, the next one, I have a 0. Notice it went from increasing to decreasing. So I must have a relative max at the point x equals -1. Or I could say -1, 4. I actually already plugged in and found the y. Next piece, from -1 to 0, it's negative, means it was decreasing in a shape of concave down. Next, the point 0, 0, 2, what's happening? 0, 2, down here, there's a 0, and it went from minus to plus. It went from concave down to concave up, which means this is a point of inflection. Next, minus plus. That means we were decreasing in a concave up shape. The 0 here, we were decreasing and then increased, so this must have been a relative min. And then finally, plus plus. The first plus meant we were increasing. The second plus means we were concave up. By the way, the relative min coordinates was 1, 0. Now let's try and sketch the graph. So when I try and sketch my graph, I look for the biggest numbers in my table, and the biggest number in my table is 4. So maybe just mark 4 marks along your axes everywhere. Plot any points that you know, for instance, any x-intercepts, which we didn't know, and then plot your y-intercept at 0, 2. Plot any relative mins and max and points of inflection. -1, 4 was a relative max, and 1, 0, a relative min. Point of inflection at 0, 2. Finally, we're going to draw the pieces of our graph. From -infinity, you're going to graph pieces of curve like this. So for the first portion, -infinity until -1, this point should have been here, by the way, you're going to draw a piece of graph that is increasing in a concave down shape. So you want to be going up in a sad face. You're going to continue sad face, but now we're decreasing from -1 to 0. Then from 0 to 1, you're decreasing still, but in a concave up face, so a happy face. And then finally, we're increasing in a concave up face. Make it happy face and shoot upward. So I am looking to see that you are in this sad face, and we convert to this happy face here. And these points should be quite visible. Any questions, please have them ready for the next day of class. Thanks.